I'm John Koza from Stanford University. Genetic programming is a systematic method for automatically creating a computer program to solve a problem. There are now 36 instances where genetic programming has produced a human competitive result. The most important point of our fourth book on genetic programming is that genetic programming now routinely delivers high-return human competitive machine intelligence. The second of our book's four main points is that genetic programming can be used as an automated invention machine. Genetic programming has created 11 entities that infringe previously issued patents, 10 entities that duplicate the functionality of previously issued patents, and 2 patentable new inventions, including this general-purpose controller that outperforms controllers that are currently in widespread industrial use. 6 of these 23 patents were issued after January 2000. The book's third main point is that genetic programming can automatically create a general solution to a problem in the form of what we call a parameterized topology, a term that we'll explain later. The book's fourth main point is that, summarizing work over the 15-year period between 1987 and 2002, genetic programming has delivered a progression of qualitatively more substantial results, in synchrony with 5 approximately order of magnitude increases in the expenditure of computer time. The 5 now identifiable groups of ever better results include solving toy problems of the 1980s and early 90s from the field of artificial intelligence and machine learning, producing human competitive results not involving patents, duplicating or infringing 20th century patents, duplicating or infringing 21st century patents, and creating patentable new inventions. The book and this video present results covering a variety of structures, including controllers, antennas, genetic networks, networks of chemical reactions, and analog electrical circuits, including the creation of circuit placement and routing simultaneously with the creation of circuit topology and sizing. If you are not already familiar with the flowchart and operation of genetic programming, a short introduction is available through the DVD menu. The purpose of a controller is to force a system, called the plant, to produce an output signal that matches a specified reference signal. For example, the cruise control device in an automobile generates a signal that causes fuel to flow into the automobile's engine, that is the plant, so as to reduce the difference between the car's current speed, the plant output, and the desired speed, that is the reference signal. Negative feedback occurs when the plant output is fed back to a controller and subtracted from the reference signal. This controller has a proportional gain block that amplifies the difference between the fed-back plant output and the reference signal, and a block that separately amplifies this difference and integrates it with respect to time, and a derivative block that differentiates yet another amplified difference. This controller is called the PID controller because the output of its proportional block, integrative block, and derivative block are added together to produce the controller output. Genetic programming can be used to automatically synthesize a controller's topology and its numerical parameter values, that is, its tuning. Prior to launching a run of genetic programming, the human user specifies the function set, the terminal set, the fitness measure, control parameters such as the population size, and the termination criteria. For a problem of controller synthesis, the function set may consist of generic ingredients such as proportional gain, integration, and differentiation, leads, lags, and delays, and addition and subtraction. The function set may also include automatically defined functions that are dynamically added and deleted during the run by the architecture-altering operations. The generic terminal set contains the controller's 2 inputs, namely the plant output and the reference signal. Suppose the plant that is to be controlled consists of 2 lag blocks and a protective front-end limiter. The fitness of a controller is typically couched in terms of a combination of time domain and frequency domain considerations. In this problem, we seek to minimize the integral of the time-weighted absolute error between the plant's actual response and the desired response, to minimize the amount by which the plant output overshoots the desired value, and to require that the controller operate robustly in the face of significant variation in the plant's parameters. This genetically evolved controller brings the plant up to the desired level with only 41% of the integral of time-weighted absolute error of a PID controller tuned using conventional methods, and has considerably less overshoot than the conventional controller. The genetically evolved controller also has the unrequested virtue of rejecting disturbance better than the conventional controller. This genetically evolved controller is the PID D-squared controller patented by Harry Jones in 1942. In other controller synthesis problems, genetic programming rediscovered the familiar PID controller patented by Callender and Stevenson in 1939. Other considerations such as stability, bandwidth, and energy costs can be included in a controller's fitness measure. In evaluating an automated problem-solving method, the question naturally arises as to whether the method produces results of any substance. We say that a result is human competitive if it satisfies at least one of 8 specific criteria itemized in our book. These criteria are all at arm's length from the field of artificial intelligence, machine learning, and genetic programming, so that the result cannot acquire the rating of human competitive merely because it is considered interesting by researchers inside these specialized fields. For example, one of the 8 criteria is that the machine-produced result is publishable in its own right as a new scientific result, independent of the fact that the result was mechanically created. Another is that the machine-produced result was patented in the past or would qualify today as a patentable new invention. The foregoing genetically evolved infringements of the Jones patent and the Callender and Stevenson patent are therefore human competitive, and also satisfy Arthur Samuel's goal for the fields of machine intelligence and machine learning. Another question that arises in evaluating an automated problem-solving method concerns how much is actually delivered by the automated operation of the artificial method in comparison to the amount of knowledge, information, analysis, and intelligence that is pre-supplied by the human employing the method. We define the AI ratio, that is the artificial to intelligence ratio, as the ratio of that which is delivered by the automated operation of the artificial method to the amount of intelligence that is pre-supplied by the human. By defeating the world chess champion in 1997, Deep Blue delivered a high amount of A in the form of a milestone human competitive result. However, because of the numerous person years of human I invested in its highly specialized chess-playing software and hardware, Deep Blue has a low A to I ratio. Manifestly, the aim of the field of machine intelligence is to get computers to automatically generate human competitive results with a high AI ratio, and not to demonstrate that humans are capable of producing human competitive results themselves. The amount of A in the numerator of the AI ratio is high for the genetically evolved controllers that infringe previously issued patents. On the other hand, the human user pre-specified only a de minimis amount of knowledge, information, analysis, and intelligence as part of the preparatory steps prior to launching the run of genetic programming. Specifically, genetic programming was not supplied with any domain knowledge about controller synthesis, or any significant domain knowledge about controllers, such as the usefulness of negative feedback. The function set and terminal set were platitudinous and contained only generic ingredients applicable to a broad range of controllers, while the fitness measure was simply a mathematical calculation for evaluating whether a candidate controller has the desired high-level behavior. The problem's fitness measure merely specified what needed to be done and not how to do it. Therefore, the amount of human-supplied I in the denominator of the AI ratio is decidedly low, and the genetically evolved results have a high A to I ratio. Genetic programming has similarly automatically synthesized controllers that outperform human-designed controllers for a 3-lag plant, a non-minimal phase plant, and a 3-lag plant with a 5-second delay. Another question that arises in evaluating an automated problem-solving method concerns whether the method is routine. Routineness means that the method is general, and that relatively little human effort is required to get the method to successfully handle new problems within a particular domain and new problems from a different domain. The transition from one controller synthesis problem to another is accomplished merely by changing the fitness measure. Because little human effort is required to make this transition, the transition is considered routine. The topology and sizing of structures, such as antennas, can also be automatically synthesized by means of genetic programming. For example, a two-dimensional wire antenna can be constructed by a turtle that starts at a particular point, facing in a certain direction, and drops metal while moving a certain distance, then turns to a new direction, moves a certain distance without dropping metal, then turns again and moves in the new direction while dropping metal, and again turns and moves while dropping metal, yielding this final small antenna, whose patterns of gains in various directions are shown at the right. In a run in which fitness was a linear combination of gain and voltage standing wave ratio, progressively better and better antennas emerged during the run, finally yielding this high fitness antenna employing the Yagi-Yuta topology. Genetic programming automatically discovered the antenna's topological features, such as the number of wires, the fact that each wire would be straight, the fact that the wires would be arranged in parallel, as well as the antenna's sizing, that is, the wire spacing and length. The transition of a problem of controller synthesis to one of antenna synthesis is accomplished by replacing primitive functions and terminals appropriate for controllers by ones appropriate for antennas, and replacing a fitness measure couched in terms of controller behavior by one couched in terms of antennas. Because little human effort was required to make the transition between domains, the transition is considered routine. Other transitions between problem domains are similarly routine in this video and our book. Three-dimensional antennas can be created by employing a flying turtle, and an enormous variety of other types of complex structures can be similarly created using Linden-Meyer systems, the Logo programming language, and other grammatical and developmental techniques. Many problems in science in general, and bioinformatics in particular, involve automatically inferring both the topology and sizing of an unknown system from observed data. For example, this metabolic pathway has two externally supplied substances, 4 chemical reactions, one of which consumes 2 substrates as its inputs, while producing 1 intermediate substance as its output, whereas this reaction consumes 1 substrate while producing 2 substances. This metabolic pathway contains several noteworthy topological features, including a bifurcation point that distributes a substance to a first reaction and also to a second reaction, and an accumulation point that takes glycerol from an external source, as well as an internal reaction that produces it. There's also an internal feedback loop that consumes glycerol and also produces it. This network, whose output is shown here, is part of the phospholipid cycle that produces the substance that self-assembles into the cell wall. Chemical reactions are governed by rate laws, such as the Michaelis-Menten law for one substrate reactions and pseudo first and second order rate laws. Networks of chemical reactions can be interchangeably represented by diagrams, program trees, Lisp symbolic expressions, systems of nonlinear differential equations, and analog electrical circuits. In a run of genetic programming used to reverse engineer a metabolic pathway, there was a progression of improved pathways. This one consumes only one of the two relevant inputs and has only one intermediate substance, whereas this one consumes both relevant external substances. This one has an internal feedback loop and the correct total number of reactions. However, the number of reaction substrates and products are not correct. This pathway has the correct overall topology, but incorrect rate constants. And finally, this pathway, at generation 225, has both the correct topology and sizing. This genetically evolved network for the synthesis and degradation of ketone bodies has two bifurcation points, two accumulation points, and one internal feedback loop. Genetic programming can also automatically infer both the topology and sizing of a genetic network, such as this one, shown here in the form of a Lisp S expression created by genetic programming, and shown here in C-style pseudocode. Our approach to automatic synthesis of the topology and sizing of electrical circuits draws on another biological process, namely the developmental process by which an embryo develops into a fully grown organism. An electrical circuit can be grown by progressively executing circuit constructing functions in a program tree. A circuit's placement and routing can be synthesized at the same time as its topology and sizing by using geographically aware circuit constructing functions. The geographically aware functions keep track of the geographic location of each component and wire during the developmental process. This process starts with a modifiable wire Z at a particular geographic location on the circuit board or chip, and an incoming signal V, a source resistor, and a load resistor. The circuit constructing program tree contains component creating functions, topology modifying functions, development controlling functions, and numerical constants and arithmetic performing subtrees that establish component values. This inductor creating function inserts L2 in lieu of a modifiable wire, while appropriately adjusting the location of pre-existing wires and components. This parallel division function duplicates inductor L2 and creates two modifiable wires. Two polarity reversing flips and one development controlling end bring this path through the program tree to an end. This capacitor creating function converts an inductor into a capacitor, whose component value is established by a 7-point arithmetic performing subtree. This series function divides a modifiable wire. This capacitor creating function inserts a capacitor in lieu of a modifiable wire. This topology modifying function creates a connection to ground, and this inductor inserting function converts a modifiable wire into an inductor. The result is the topology, sizing, placement, and routing of a fully developed circuit. Using a fitness measure that includes the area of the bounding rectangle, in addition to the behavioral requirements of a low-pass filter, genetic programming first synthesized the topology, sizing, placement, and routing of a 100% compliant filter, and then reduced the area and reduced it yet again. Genetic programming similarly synthesized a 60 decibel amplifier containing transistors with a smaller and smaller footprint. There are numerous instances where genetic programming has duplicated the functionality or infringed a previously issued patent, including the Philbrick circuit, an analog circuit performing the digital NAND function, and analog computational circuits. Genetic programming easily evolved a circuit rediscovering the concept of negative feedback, famously invented by Harold Black of AT&T in 1927 during a ferry boat ride across the Hudson River, in which he conceived the idea and scribbled it onto a page of the New York Times. Black's landmark invention was delayed in the U.S. Patent Office for 9 years because, as Black later recalled, it was so contrary to established beliefs, namely the nearly universal idiom of positive feedback championed by Edwin Armstrong of Westinghouse. Even after AT&T had been operating long-distance telephone equipment using Black's invention for many years, the British Patent Office treated Black's patent application in the same manner as one for a perpetual motion machine. We believe that one reason why it took so long for negative feedback to gain acceptance is that human thinking often becomes channeled along well-traveled paths of established beliefs. One of the virtues of genetic programming is that it is not aware, much less concerned, with whether a solution is contrary to established beliefs. For this reason, genetic programming often unearths solutions that might never occur to a human engineer. Genetic programming has duplicated the functionality, or infringed, 6 analog circuits patented after January 2000, including a low-voltage balance circuit suitable for contemporary wireless communication needs, a variable capacitor circuit, a voltage current conversion circuit, a low-voltage high-current load circuit for testing a voltage source, a low-voltage cubic function generator, and a tunable integrated active filter. To emphasize the routineness of genetic programming in generating human competitive results based on 21st century patented inventions, we approach these 6 problems with the same embryo, the same program architecture, the same function set, the same terminal set, the same minor control parameters and termination criteria, and the same parallel computing arrangement, so that the only material difference from problem to problem was the fitness measure representing the high-level statement of the problem. The key difference that the inventor identified between previously known balance circuits and his own invention in 2001 was a coupling capacitor attached to the collector and base of a particular transistor. Our genetically evolved balance circuit contains the same key feature. The genetically evolved circuit not only duplicates the functionality of Lee's patented circuit, but is a 4-fold improvement in terms of the problem's fitness measure and has better high-frequency response. Curiously, even though the genetically evolved circuit possesses the feature identified by the inventor as the essence of his invention, and additionally possesses 3 specific features enumerated in the patent, it does not infringe Lee's patent because of the absence of yet another specific feature. In the foregoing run, we did not specifically request that genetic programming engineer around Lee's patent. However, if our specific intent had been to avoid infringing a pre-existing patent, the fitness measure could have included a penalty for using any identifiable feature enumerated in Lee's patent. Alternatively, if our intent had been to generate a new invention, the fitness measure could have penalized the use of the key features of any already known solution. Our genetically evolved variable capacitor circuit possesses most, but not all of the elements of the claims of the post-2000 patent, and therefore does not infringe. The genetically evolved solution to the high current load problem bears hardly any resemblance to the patented circuit. The genetically evolved voltage current conversion circuit duplicates the functionality of the patented circuit using an entirely different but readily understandable approach, whereas the genetically evolved cubic signal generator has considerably less error than the patented circuit, but is not readily understandable. Our first genetically evolved tunable integrated active filter performed slightly better than the patented circuit. However, it used an excessive number of components. When we reran this problem with parsimony in the fitness measure, the resulting genetically evolved circuit squarely infringed the patent. 100% of our runs involving the post-2000 patented circuits produced a satisfactory solution, suggesting that we have not yet reached the boundary of genetic programming's capacity as an automated invention machine. A parameterized topology is a general solution to a problem in the form of a graphical structure whose nodes or edges represent components, and where the parameter values of the components are specified by mathematical expressions containing free variables. Genetic programming created this parameterized topology for a filter circuit in a single run that determined the circuit size, connectivity, and component types, capacitors and inductors. Genetic programming also created mathematical expressions that established the parameter values for the components, such as the capacitance of each capacitor and the inductance of each inductor. The free variables in the genetically created mathematical expressions confer generality on the solution by enabling a single graphical structure to represent a general solution to an entire category of problems. For example, if the free variable representing a filter's cutoff frequency is 1,000 Hz, the circuit's components take on these numerical values. But these values for 3162 Hz, these for 10,000 Hz, these for 31,620 Hz, and these for 100,000 Hz. If the genetically evolved program additionally contains conditional developmental operators, different graphical structures may be produced for different instantiations of the free variables. That is, the program may operate as a genetic switch, switching, for example, from this topology for a low-pass filter to this entirely different topology for a high-pass filter. Genetic programming can also create parameterized topologies for general-purpose controllers. Using 8 separate simulations on each of 24 plants from Asterman-Hagelin's industrial representative family of plants, genetic programming created a parameterized topology for a general-purpose controller that outperforms PID controllers tuned with the widely used Ziegler-Nichols tuning rules and with the recently developed Astrom-Hagelin tuning rules. As part of an integrated process, genetic programming determined the controller's size, connectivity, and component types, such as adders, subtractors, constant gains, parameterized gains, and lead blocks. This integrated process also created mathematical expressions that established the parameter values for the amplification factors for both of the controller's parameterized gain blocks, and the time constant for both of the controller's lead blocks. The free variables in the genetically evolved mathematical expressions confer generality on the genetically evolved solution. Other genetically evolved general-purpose controllers use lag blocks rather than lead blocks. All three are novel non-PID topologies. Averaged over 18 previously unseen plants used for cross-validation, this genetically evolved controller has, in comparison to the Astrom-Hagelin controller, 64% of the set point integral of time-weighted absolute error, 85% of the ITAE associated with disturbance rejection, and better minimum attenuation and maximum sensitivity. Controller design is important because a small percentage improvement in the operation of plants may translate into significant economic savings. The transition from synthesizing controllers for single plants to synthesizing parameterized topologies merely entailed adding free variables to the terminal set and evaluating candidate controllers over a set of plants. Genetic programming has also evolved tuning rules for PID controllers that outperform conventional tuning rules. For over 200 years, the U.S. Patent Office has been in the business of receiving written descriptions of human-designed inventions and judging whether the purported inventions are new, improved, useful, and unobvious to a person having ordinary skill in the art. In the years to come, we believe that genetic programming will be increasingly used as an invention machine to generate patentable new inventions. In fact, we have recently applied for a patent on the previously described general-purpose controllers and tuning rules. Summarizing the work covered by our 4 books on genetic programming over the period from 1987 to 2002, we can see that genetic programming is not limited to solving just a single problem, or problems from just one particular domain, and did not top out after solving toy problems. Moreover, genetic programming has been able to take advantage of the increased computational power available by means of parallelization, and thereby avoid a pitfall that often constrains other proposed approaches to machine intelligence. Looking back, we can now see that genetic programming has been able to deliver qualitatively more substantial results as a result of exponentially increasing computer power made available by the relentless iteration of Moore's law. Specifically, there have been 5 approximately order of magnitude increases in computer speed as we moved from our first computer, a serial list machine, to a parallel network of 8-bit transputers, to a 64-node parallel network of 80 megahertz processors, to a 70-node system of alpha processors, to a 1,000-node system of 350 megahertz Pentium 2 processors, and finally to substantially longer 4-week runs on the 1,000 Pentium system. These order of magnitude increases in computer power correspond closely to a now identifiable progression of qualitatively more substantial results, including solving toy problems from the field of artificial intelligence and machine learning, producing human competitive results not involving patents, duplicating 20th century patented inventions, duplicating 21st century patented inventions, and generating patentable new inventions. This historical perspective establishes the 4th main point of our book, namely that genetic programming has delivered a progression of qualitatively more substantial results in synchrony with 5 approximately order of magnitude increases in the expenditure of computer time. The ability of genetic programming to produce these results stems from a combination of capabilities, many unique to genetic programming, starting with its ability to dynamically determine the size and shape of the solution during the run. Anyone who has ever looked at the blueprint for a building, an electrical circuit, a corporate organization chart, a musical score, a city map, a protein molecule, or a computer program will be struck by the massive reuse of certain basic substructures within the overall structure. Indeed, complex structures are almost always replete with modularities, symmetries, and regularities. Genetic programming can reuse code by means of automatically defined functions, automatically defined iterations, automatically defined loops, and automatically defined recursions. And genetic programming can also reuse the result of executing code by means of automatically defined stores. Reuse avoids reinventing the wheel on each occasion requiring a particular sequence of already learned steps. We believe that reuse is the cornerstone of meaningful machine intelligence. Genetic programming is also able to dynamically determine during the run the number of reused structures, their type, and the nature of the hierarchical references among the substructures. Genetic programming can also dynamically discover the dimensionality of substructures and pass parameters to them. In addition, genetic programming can use a developmental process to maintain validity and locality and discover general solutions to a problem in the form of a parameterized topology containing free variables. The architecture-altering operations, patterned after the naturally occurring genetic operations of gene duplication and gene deletion, provide the mechanism for the dynamic self-organization of hierarchies during the run of genetic programming. For example, when genetic programming synthesized a double bandpass filter, the architecture-altering operation is dynamically determined during the run that the evolved circuit would contain 4 occurrences of the 3-ported automatically defined function ADF0 and 2 occurrences of the 4-ported automatically defined function ADF3. When genetic programming synthesized a crossover filter, the architecture-altering operations dynamically created the hierarchy shown by this call tree, consisting of 3 different subroutines, including 2 occurrences of ADF3, 4 occurrences of ADF2, 1 occurrence of ADF4, and 3 instances of one subroutine hierarchically calling another. This automatically defined function contains capacitor C39, whose component value is established by a dummy variable arg0 that is passed into this automatically defined function. All of the foregoing substructures, all of the hierarchy, and all of the reuse were automatically and dynamically determined by the architecture-altering operations during the run of genetic programming, not by the human user. We believe that the ability of genetic programming to routinely deliver high-return human competitive results stems from 7 specific differences between genetic programming and other proposed approaches to automated problem solving. Many computer scientists unquestioningly assume that automated problem solving processes must necessarily be logical and deterministic. However, neither of these 2 characteristics govern 2 of the most important processes for solving complex problems, namely the invention process performed by creative humans and the evolutionary process occurring in nature. A new idea that can be logically deduced from facts that are known in a field, using transformations that are known in a field, is not considered to be patentable by the Patent Office. A new idea is patentable only if there is an illogical step, that is, a logically unjustified step. Interestingly, everyday usage parallels the law concerning the point that a lack of logic is a precondition for a patent. People who mechanically apply existing facts in well-known ways are summarily dismissed as being uncreative. Inventions created by genetic programming exhibit the same kind of creativity, logical discontinuity, and departure from established ways of thinking that are the essence of invention. The evolutionary process is probabilistic rather than deterministic, and it is certainly not guided by mathematical logic. Indeed, one of the most important characteristics of the evolutionary process is that it intentionally creates and actively encourages inconsistent and contradictory alternatives throughout the process. In fact, the active maintenance of inconsistent and contradictory alternatives, called genetic diversity, is necessary for successful evolution. Evolution certainly does not rely on a domain knowledge base. Furthermore, evolutionary search does not rely on greedy hill climbing or point-to-point search. The population enables genetic programming to explore a mathematically principled number of adventurous possibilities while simultaneously exploiting the immediately gratifying avenues of advance through the search space. In addition, genetic programming overtly conducts its search in the space of computer programs. Finally, genetic programming differs from other proposed approaches to automated problem solving in that it is biologically inspired. It is a system that works based on a system that works. Looking forward, we believe that genetic programming will be increasingly used to automatically generate ever more complex human competitive results. As far as we know, genetic programming is, at the present time, unique among methods of artificial intelligence and machine learning in terms of its duplication of numerous previously patented results, unique in its generation of patentable new results, unique in the breadth and depth of problems solved, unique in its demonstrated ability to produce parameterized topologies, and unique in its delivery of routine, high-return, human competitive machine intelligence.